Welcome back to today's video. In today's video, we're going to discuss how we can display correlation between the different pairs of attributes in our training data, visualizing that correlation, as well as interpreting what the correlation is. And in our last lesson, we discussed how we could exactly visualize our longitude, latitude, median house value, as well as population size for each of the individual districts. Let's get right into today's video. All right, so in the last lesson, remember what we discussed was we basically compared the longitude and latitude at different points here in California when we were comparing them. And remember what these dots represent is each of the dots represent individual districts. And so what we saw there is that many districts occurred at a latitude of 38 to 36 and a longitude of negative 123 to negative 122. And you could also say that about this particular interval as well, from negative 119 to 118, and a latitude of 34 roughly. And so when you're seeing here, as the opacity here increases, that is emblematic of the fact that there are going to be more districts in those particular areas. And so we discussed how we could visualize that longitude and latitude. We also discussed how we can visualize our median house value as well as the population. And so what we used was we used the plot function and use that for our housing data frame object. And what we showed was that as the dots get bigger for each of the individual districts, and remember each dot represents an individual district, that means the population size is bigger. And what we also showed was that this color bar on this side, which we displayed by setting the color bar parameter equal to true, represents how expensive each of the houses are by using a jet color. And so you're seeing here that as the color goes further to the red, it becomes more expensive. As it goes further to the blue, it becomes cheaper. And so you're seeing that many of the areas here are more cheaper. Many of the areas near the coast are less cheap. And we visualize this as the shape of California because our X and Y values were the longitude and latitude, which is why it looks similar to how California would look on a geographical map. But in today's video, what we're going to take a look at is how exactly we can compare the data using the Pearson-R correlation coefficient. The Pearson-R correlation coefficient is a standard correlation coefficient that displays and calculates the linear relationship between two particular attributes. And what this number will return is it will basically return a number that is within a range of negative 1 to 1, 1 being a strong positive correlation, while negative 1 indicates a strong negative correlation, while 0 indicates a correlation of nothing. Now, what is a positive correlation? A positive correlation simply indicates that as one value goes up, the other value also goes up. A negative correlation would indicate the fact that as one value goes up, the other value goes down. A correlation of 0 indicates that there is really no correlation that you can draw between the two attributes under consideration. The chart here, the image that we have here really displays how this would look like graphically. So you can see that a correlation of 1 indicates that as one attribute goes up, the other attribute goes up as well. That would be a correlation of 1, and that's typically represented by a straight line. 0.8 indicates that it's still a very strong correlation, although as you can see, the values are not lining up with each other exactly. And then you have a correlation of 0.4, which indicates that the data is more scattered out and the variance of that data is much bigger. A correlation of 0 really indicates that there's no correlation whatsoever. And then negative 0.4 is basically the same thing as positive 0.4, except it's in the opposite direction because of the fact that as one value goes up, the other value goes down. Now, whenever we have a correlation of 1 or a correlation of negative 1, typically speaking, that only occurs when we're comparing a value to itself. And so if we were to compare the longitude to the longitude, that would always return a correlation of 1. And so typically speaking, we'd only get a correlation of 1 if we're comparing a value to itself. And so you're able to see there what those correlations would look like. And remember, these are only for linear correlations, which is why the correlations here at the bottom are not linear correlations. Therefore, all of them were assigned a correlation of 0. Going back here to our notes here, let's take a look at how exactly we can visualize this. And remember, it's going to return values. The Pearson-R correlation coefficient is going to return values within a closed interval of negative 1 to 1. Okay? And so what we'll do here is, first of all, let's go ahead and take a look at our housing data. Now, remember, our housing data is just our test data. It's not our entire data. And so remember, going back to our housing.csv file, we're noticing here that our entire data was roughly around 20,000 entries, 20,000 data instances. But in our case, our housing data frame in this case will not be the entire 20,000. it'll only be roughly 16,000. Because remember, we reset the housing data frame object, I believe in our last lesson or in the lesson before, or yeah, in our last lesson, where we said that the housing data frame object was equal to the stratified training set. And so it's only equal to roughly 80% of our entire data set. And so because of that, our housing object now will have 16,000 instances, not 20,000 instances. But the 16,000 instances that we have will be highly resemblant of the entire data set. So the 16,000 instances will be very similar to all the data sets. And so that's very important because of the fact that we stratified that data, and we discussed that in tutorial number 9. So going back down here, let's take a look at what this correlation coefficient is. So remember, this is our housing data frame, and let's go ahead and first of all start off by printing that. Just go ahead and print that out. And what we see there is we got roughly 16,000 rows with 11 columns, and the 11 columns will still be preserved. Now, when you're looking at this, you're noticing that the correlation coefficient only works with numerical values. It only works with numerical values. And so when you're looking at this data, you're noticing here that the ocean proximity cannot be considered due to the fact that it is actually an object. The ocean proximity, while it may look like a string, the values are actually object data types. And obviously, the Pearson-R correlation coefficient cannot determine cannot determine the correlation between strings or objects. And so we obviously have to remove that particular value from our consideration. We also have the income underscore cat, which remember we calculated that before and we added that to our data frame a while back. So let's go ahead now and run this function here. So let's take a look at this. We have our housing dot drop. So what we first did was we removed the ocean proximity from our matrix. And the reason for that was obviously is because this particular correlation coefficient only measures the correlation between numerical attributes. So we removed that particular column from our housing data frame. And then we're going to call the core function, which is going to calculate the correlation between each of these values. And you'll basically see that this will be a matrix where you'll have a column values, and you'll also have row labels. So you'll have row labels and column labels, and I'll explain how this all relates together. So let's go ahead and print out our correlation matrix. Let's go ahead and print that out at this time. So when we print it out, we notice a couple of characteristics. First of all, we notice that we have row labels on the left-hand side, and we also have column labels on the top of each row. Now, the reason why it's moving to 3 different row spaces is because of the fact that we simply cannot fit all the data in one particular row. And we showed that out. You saw that in other videos. But let's take a look at what this data is. You notice here, let's take a look at our first entry here. We notice that we have longitude as being our Y label, or not our Y label, but our column label. And we have longitude as being our row label. And we notice that when you map this, you get a correlation of 1. And a correlation of 1, if you remember, is a very strong correlation. It's basically just a straight linear line. So it's typically can be represented by an equation y equals mx plus b. And why is that the case? Well, it's because of the fact that as longitude increases by the exact same value, right? If the longitude is 34, then the longitude must be 34. And when the longitude is 35, the longitude must be 35. And so it's going to be exactly the same value, all right? But, and so even if you notice some of the other attributes, you notice here, total bedrooms. Compare total bedrooms to total bedrooms right here. That's going to be a correlation coefficient of 1. You go down here, median house value. Compare that to median house value, that's going to be 1. Okay, you compare income underscore cat to income underscore cat, you get 1. Okay, so you're noticing there that if it's the same attribute, it's going to be the same correlation coefficient. But let's take a look at some of the other attributes. Let's move away from actually a longitude and housing median age. Let's take a look actually at median income and compare it to our median house value. So median income and median house value. So when we map that and just take a look at that, we get a 0.7% correlation. So basically there's a 70% correlation. Taking a look here at our at what we're looking at here, you're noticing that that's a pretty good correlation, right? 0.7 is going to be a pretty good correlation. It's near 0.8, so that's a fairly stable correlation there. So 0.7 is a good correlation. And so you can see there that as median income goes up, right, as the median income for the districts. Remember, these are not people, these are districts. Now, districts are made up of people, but what we're comparing here are districts, right? And districts are made up of a bunch of people, right? And so what you're noticing here is that as the median income for different districts goes up, the median house value will also go up, because typically speaking, if people have a bigger income, they can buy a bigger house. And so that would be, or a more expensive house. And so that would be something that we would probably anticipate, right? And so you're seeing that there. You're seeing your total number of bedrooms. Now, this is important because when you see total number of bedrooms, you might think, okay, so a house might have 5 bedrooms or 10 or like 2 bedrooms. Well, remember, these are the total bedrooms for the entire district, right? And so typically speaking, the total bedrooms for an entire district, what you would do is you would basically add up the total bedrooms in every single house. And so let's go take a look at how many total bedrooms there are normally in our CSV file here. Let's take a look at total bedrooms. You're seeing here that for many of these districts, 300 total bedrooms, right? One district is actually 17 total bedrooms, which means that there's probably very few houses in that district. But in this district here, 416 total bedrooms, right? And so you're seeing that it's for the entire district, right? And so that's important for you to make sure you know that. All right? So we notice that those correlation coefficients are very valuable. And we're basically comparing two of those attributes there. Now, with that being said, what we're going to go ahead and do is take a look at a particular attribute. Let's take a look at a particular attribute, and it's the attribute of comparing the median income to the median house price. So let's go ahead and comment this out, and let's uncomment this out. What this code does is it takes the correlation matrix, and it takes the median house value, and we can just display that, but what it's going to do is it's going to sort it it's not going to sort it in ascending order, it's going to sort it in descending order. All right? Let's go ahead and print that out. And when we print this out, it's taking a look at a particular characteristic. Now, remember, in this case, the column name is going to be median house value, right? And the easy way for you to determine that is just by looking at this. Median house value has a value of 1. Well, if the median house value has a value of 1 from the labels on the left-hand side, on the column names, it would also expect to have a median house value of 1, since the correlation would have to be 1. But let's take a look at this particular one and notice that it's sorted in descending order there. And so let's take a look at this median income. We already covered that. We noticed that there's a strong correlation between the median income of a particular district as well as the median house value. We notice here for the total rooms. A total rooms actually is not a very good determiner of the house value, and we're going to look at that a little bit later. But just keep that in mind. Total rooms is not really a good indicator of how much the house value is in that particular district, just because of the fact that let's say you had, let's say a very residential area, there might be more homes in that residential area, but that doesn't mean that the house prices in that residential areas is higher, right? Let's say you had a district with 500 homes, right, that were worth $200,000 each on average. Well, in that case, the median house value would be 200,000, right? On the other hand, let's say you had a district with 5 homes, but each of those homes were worth, let's say, $1,000,000. Well, the median house value would be $1,000,000, yet the number of rooms in those 5 houses would be, let's say, 50. So a district with 50 homes, 50 rooms in total, would have a higher median house value than a district with 500 homes, with which let's say that would be like I don't know, 2,500 rooms, right? And so the total number of rooms would not be a good determiner of the median house value, which is why this value is ranked so low. And we're going to actually show a graph explaining this, and you can easily visualize this. And so you see, going down the list, you can look at the individual factors as well. And so that's how we could do that there. With that being said, now let's take a look at how we can visualize the correlation. So right now we just looked at it from a total numerical lens. Let's take a look at how we can visualize this correlation. So we notice here that we have here a scatter underscore matrix. And what this function does is it basically creates a graph comparing each attribute that we listed to all other attributes, including that attribute, in a graph format. And it displays all of them, similar to how we did it for a histogram, I believe, maybe in tutorial 4 or tutorial 5. But what this does is we see here from pandas.plotting import scatter underscore matrix, we have our different attributes that we want to consider. And you're noticing here that we have a good conglomeration of about 4 of those particular attributes. And then what we're saying is scatter matrix considering the housing attributes, right? And we're basically attributes, we're sending that in we're not sending that in. We're selecting those particular columns in the housing data frame, and we're saying that we're going to create a particular number of graphs. And once we have all those graphs, it's going to have a width of 12 and a height of 8. Okay. Now keep in mind here, how many graphs are we going to generate? If our goal is to compare each attribute to all other attributes, we have roughly 4 attributes, right? And so if we're going to compare each attribute to every other attribute, including that attribute, well, we're going to have 16 graphs that are generated. So for median house value, we'll have a graph comparing median house value to median house value. We'll compare it to median income. We'll compare it to total rooms. We'll compare it to housing median age. And then for median income, we'll compare it to median house value, to median income, to total rooms, to housing median age. Now that we're considering this from a graphical perspective, what do you think the graph for median house value would look like? Well, obviously, it would be a straight line. It would be a straight line starting from the bottom left going to the top right. That being said, pandas basically knows that if you're comparing a value to itself, it's going to have a correlation coefficient of 1. And so because of that, it actually does not create a correlation graph. Instead, what it does is it actually shows how many districts represent that particular quality, and it shows a histogram for that. And so that's going to be very helpful for us. Let's go ahead and run this particular piece of code, and let's go ahead and see what we get as the output. All right, so it looks like we're just printing out the, all right, good. It's, I don't know why it went to the print function. All right, so all right, so let's go and take a look at this. So let's take a look at what our data looks like. So you're noticing here that this is similar. It's a little bit different from the values, but let's take a look at this. So we have here median house value, and we're comparing that to median house value. And obviously that would have a correlation coefficient of 1. So that would be typically a straight line. It would be a straight line because none of the values would be different. But in this case, it's going to be a histogram. And the reason for that is because it knows that it's going to have a correlation coefficient of 1. And so it's showing how many districts represent that particular value. And so you're seeing that a lot of districts here, the plurality of districts, have a value, have median house value above 400,000. That's what it shows there. The plurality of districts have that particular median house value. The minority of districts have a house value of like under 100,000. The minority, the least, when you compare it to all of them, right? And so you're seeing that there. Now you're also seeing that for the median income when you compare that to the median income, right? If you map it here going up and then going across, see where those intersect. You're noticing here that very few districts here that have a median income that is going to these high levels, okay, going to these higher levels over here, since the number decreases, right? In terms of the number of districts, the median income goes down. Yeah, the number of districts with that median income goes down as the median income goes up. All right, and so you're seeing the same thing for total rooms, and you're seeing the same thing for housing median age. Now let's take a look at the graphs that we're really concerned with. Let's take a look at this graph right over here, median house value, and then we'll compare that to the total rooms. So what we can observe there, let me go ahead and zoom out a little bit just so that we can see all of these. What we're noticing here is that, let me go down a little bit. Okay. So what we're noticing here is that a lot of districts have a total number of rooms that is less than roughly 1,500, right? And this is a rough approximation, right? Less than 1,500, the majority of rooms, a strong majority of rooms have a number of rooms that is below 1,500, or yeah, 1,500. And so what this shows is that doesn't really affect the house value. And again, we explained this before. So we're seeing here that even houses with extremely high house values, right, districts rather, have a very small number of rooms, right? And so the total number of rooms does not really predict well with the median house value. Let's take a look at the housing median age. What we're observing here is that the housing median age for a particular district and the median house value is not really correlated in any way whatsoever. If you wanted to draw some type of determination, you could notice maybe that the majority of people from the age of 20 to 40, right, buy the most expensive homes, right? And that might be something that you would expect if you wanted to draw some sort of correlation. And the majority of people from 20 to 40, roughly 18 or so, or even younger than that maybe, most of those people are the bulk of people who buy homes that are more residential homes, which is why it's more concentrated in this particular area, because the majority of people buy residential homes, which may be under $300,000, right? And you might be noticing here some trends here. You're looking at all this data, you're noticing that there's a line here at the top for all these three graphs. One of the reasons for that is because the median house value was capped at 500,000. And so any district which has a median house value above 500,000, what it's basically doing is it's lowering that value and keeping it within that interval. And that's why you're seeing that line over there. And so even if a home was worth, let's say, $1 million, what it's doing is it's lowering that and keeping it within this particular graph, which is why you're seeing that. And so essentially any home that basically is from like 490,000 all the way up to infinity, essentially, all those values are being grouped up into that one singular area. Okay, now the one that we're really concerned about is comparing median income to median house value. That's the one that we're really concerned about. And so let's zero in on that particular graph by running this particular function. Let's go ahead and zoom in a little bit just so that we can see everything. So what we'll do here is we are going to call the plot function again, and we'll say that we're going to have a scatter plot, and our x value is going to be median income, our y value will be median house value, and our alpha value will be 0.1. Remember what alpha is. Alpha basically says that if it's closer to 0, it's going to be more transparent. If it's closer to 1, it's going to be more opaque. Opaque simply meaning that it's not see-through. All right, and so we're putting it at 0.1. Now, the reason why we put it at 0.1 is because let's say we put the opacity, in this case, as being 1. Well, in that case, let's say a particular area was extremely dark. Would we be able to determine anything from that? No, we wouldn't be able to determine anything. But if we have a very low alpha value, we would be able to determine if an area was particularly dark, we would be able to determine this is a value where a lot of districts are occurring at that particular value. Whereas if we were to have an alpha value of 1, we would not be able to determine that. Let's go ahead and run this. And again, all we're going to get is the one we had above here. All right, let's go ahead and take a look at this though. All right, so let's take a look at this. So we have here median house value and we have median income. All right, now again, remember when we were running our other code, let me go ahead and show this to you. We showed that the median income and the median house value had a correlation coefficient of 0.7. And remember, this is a linear relationship. And so going back to our picture here, we can notice here that that's a very strong relationship. That's roughly 0.8, right? And so you're noticing that that's a very strong correlation. And so looking down here at this particular graph, you're noticing that again, as one value goes up, the other value goes up as well. And so it's a strong linear correlation there. And this really comes from the idea, there's different ideas that basically state in economics that as people's income goes up, their consumption goes up. And so we're seeing here that as people's median income goes up, the value of the homes that they buy also goes up in a median, like on average, basically. Median is not average, but it's an average value, right? All right, so let's take a look at this median income. So you're noticing here that we have 0, 2, 4, 6. Remember, these values are representing 10,000s, and we covered that, I believe, a couple lessons ago, or maybe in our last lesson. I believe in our last lesson. And so this would be 20,000, 40,000, 60,000, 80,000, 100,000, so on and so forth. Now, remember, this is from the 1990s, and so typically speaking, people's median incomes were much lower back then when it's not adjusted for inflation. So we're taking a look at this, and you're noticing that as people's incomes is at 20,000, the number of homes is at, as a district's median income is at 20,000, the median house value is at 100,000. And you're noticing here that from roughly 15,000 all the way to roughly 60,000, it's extremely dark. And the reason for that is because there's many districts where the median income is in between 15,000 and 60,000. And that was what our income underscore cat was representing in our last lesson. And so that's why you're seeing that it's very much darker. And that's why we set the alpha value very low in order to see if there's a very dark area, that means there's many districts that represent those particular attributes. And so you're noticing that as one data goes up, it goes up. Now you are noticing that as house prices go higher, you are noticing a bit of inconsistency here, and there's a little bit of not like symmetry there. The reason for that obviously is that as people's income goes higher, people are, there's a little bit of varying, right? Some people like to save their income, whereas some people like to spend it. And so because of that, there's a lot of varyingness to the data. All right. And also, as you're seeing there, that there's a line here at the very top. One of the reasons for that is because of the fact that, again, there are many districts with the median house value of, let's say, 600,000 or 700,000. We're just basically pushing all those down, essentially, and making sure it fits there. Also, you might be noticing that you see a line here coming right around here at 350,000. And that might throw off our model a little bit, and that might send our model the wrong signals. And so we might want to get rid of those data instances from our overall housing data frame, but also from our housing test training set as well. So we might want to get rid of some of those data instances that might be outliers and not very consistent. And you're seeing another line here a little bit coming at around 450,000. And so that's not a good idea either. And again, as incomes goes up, again, there's some people who have like an income of 100,000 who might buy houses that are only like some districts, I should say,